session we've seen about parallelogram law, then cross product, curl gradient and divergence concepts. So now we'll see some missing concepts here. So here this dot product in parallelogram law, we have developed a dot product from the two diagonals of the parallelogram, right? So here a plus b is a vector and a minus b is a vector. This is one diagonal, this is another diagonal, and the result of some operation, addition, squaring and all, we are getting a scalar out of it. So where is that conversion operation taken place? It's a matter of discussion. So we are taking vectors and we are obtaining scalar as a result. So the issue is this square operation takes care of that. Actually, you are doing a plus b vector dot product with a plus b. So you will get square of the magnitude of this diagonal. So inherently there is a dot product operation in this activity. Okay. So that is why the result is a scalar. So though you are dealing with vectors and it seems like you are squaring a vector, the result is a scalar. Okay. So another most important vector that confuses us is area vector. Like we'll be using that pressure is equal to force times area. Pressure is a scalar quantity. Force per unit area. Okay. Force per unit area. So here pressure is a scalar quantity, force is a vector quantity. So if area is a scalar quantity, if area is assumed to be a scalar quantity, then result should be a vector. Pressure becomes vector if force is the only vector quantity on the right hand side, but pressure is a scalar quantity. So what is happening there? Here area is also a vector quantity, and where from do you get that, and what is the direction of that? So area is a vector quantity obtained by taking cross product of two vectors. So area is equal to x cross y. Otherwise, if you take A and B, this is the kind of thing you may come across in your solid state physics. You may come across this. So if A is the length of the vector in one direction, maybe along x direction, if B is the length of the vector, unit vector along y direction, so then area vector is obtained by taking cross product of x component unit vector and y component unit vector. The resultant is perpendicular to the plane containing both A and B. So this is area vector. So this area vector is a pseudo vector. It is perpendicular to the plane containing both A and B. And if you want to calculate the volume is again a scalar quantity. So for that you have to multiply, or you have to take a dot product with respect to the unit vector along z direction. you must be very careful while dealing with physical quantities or in equations. Wherever you come across any set of physical quantities in equations, you must ensure the vector and scalar nature of physical quantities. So like here, force is a vector, and for general intuition, area is considered to be a scalar. For general understanding, area seems to be a scalar, but it is also a vector. So it gives information about a plane. So once you are dealing with planes, your vector must be perpendicular to the plane. So area is a pseudo vector. So resultant volume is a scalar again, which is a result of that pseudo vector dot product with the z direction unit vector. Right? So gradient generates a vector quantity from a scalar quantity. So most general statement that we come across is gradient converts scalar into vector. So that's not the fact. Here V is a scalar quantity, F is a vector quantity. So it connects a scalar quantity with a vector quantity. So it studies the spatial variation of a scalar quantity. The resultant physical quantity is a vector because the spatial variations needs a direction. So here still V is a scalar, F is a vector. So F became vector because X is a vector. So a scalar is not converting into vector. Scalar upon certain operation results in a vector. So both are different physical quantities. It is not that V is converting into a vector. V is a different quantity, F is a different physical quantity. The same way, divergence studies the spatial variations of a vector quantity. So the result is a scalar. So it is not that a vector is converting into a scalar. So this is a different physical quantity, that is a different physical quantity. They are getting connected by a mathematical operation. Right? So with that, I'm closing this session on vectors, vector algebra. Further we'll see some other basic concepts of dependent and independent variables. Right. So our next topic is dependent and independent variables in physics. So especially this Newtonian mechanics deals with cause and effect relations in physics. So that is what we see in our Newton's, let's say, second law of motion. What does it say? Rate of change of momentum is directly proportional to the force applied. So dV by dt is proportional to force. Rate of change of momentum is directly proportional to force. So here force is the cause and change in momentum is the effect. So in general, I mean, this can be written as independent variable and this is dependent. So while writing proportionalities, always you must ensure that independent variable is on right side and dependent variable is on left side. Okay. So Newton mechanics deals with that. and if you remove that proportionality constant, this can be written as dp by dt is equal to 1 by k into f. And if you fix the units, like if you take mks units, meter, kilogram and seconds, if you measure distances in meters and mass in kilograms and time in seconds, then this k becomes 1 Newton, right? It becomes 1 Newton. So in that case, this equation becomes, f is equal to k times dp by dt. Otherwise, in mks units, f is equal to dp by dt. So in any other case, you need to introduce that conversion factor in mks units. If you measure the distances in meters and mass in kilograms, time in seconds, that k becomes 1. So that k is defined as rate of change of momentum, whatever it is produced in 1 kilogram of object for within 1 second for a distance of 1 meters per second, for a velocity of 1 meter per second, this kind of thing. Okay. So this is how we write the equations. So as long as you write the equations in terms of proportionalities, you must ensure the independent variable on right side is on right side and dependent variable is on left side. Then only it will have a valid meaning in physics. You cannot write f is proportional to dp by dt and f is equal to k times dp by dt. So f is equal to dp by dt. This is not valid. This has no meaning in physics. F is proportional to dp by dt means what? Rate of change of momentum is proportional. Force is proportional to rate of change of moment. Force is proportional to rate of change of moment. And meaning evanunda? There is no valid meaning for this statement. So while using proportionalities, you must ensure this. Then only you will have a meaningful statement for that. So once you remove the proportionality, this becomes a mathematical equation. So from this stage, you can do anything you want. But while using proportionalities, you must be careful. So this has no meaning. The same way, the other is Ohm's law. V is proportional to I. V is equal to IR kind of statements will be seen in some of the textbooks. So what is that? Let's say you are taking a power supply. As long as resistance remains constant, this we have seen already in some of our previous sessions. So as long as you keep the resistance constant, more the height, more the potential, more is the current. So it is current directly proportional to voltage. More the potential, more is the current. So that proportionality constant is 1 by R into V. So V equal to IR. So this is Ohm's law. So as long as resistance remains constant, current is directly proportional to voltage. And this you can see in our previous videos. I'll attach the link. Okay. So now while drawing graphs, we must ensure that independent variable is on x-axis and dependent variable is on y-axis. So you have to always consider independent variable on x-axis and dependent variable on y-axis. This is just like y is equal to say this is x, f of x. I mean, here I is equal to function of voltage. Okay. So I mean, this we may also see in our mathematics, like domain and range. This is one way of representing the data that you collect between voltage and current. This is another way of representing the data. So always you have to take independent variable on x-axis and dependent variable on y-axis. Like let's say if you have x and sin x, so your y is sin of x. So the y variable depends upon x. So when you are plotting graph, what are you doing? You are collecting data for x versus sin x, and you are drawing it. So your domain should contain independent variable and range should contain dependent variable. Okay. But in physics there are some exceptions that we come across to this basic statement. Like stress and strain relations. Hooke's law. When you are dealing with Hooke's law, what is that happening? So you are taking a spring and you are tying a weight to it, and if you keep on increasing the weight, the length of the spring increases, and at certain time the spring will be permanently deformed. So when, up to certain extent, when you remove the weight, spring will go back to its original state, but after certain limit, spring will be permanently deformed and its length remains enlarged. So how to represent that? So what is the cause and what is the effect here in this story? So application of force. This force, downward force, which is equal to mass times the gravitational acceleration due to gravity, is the cause. So we call that as a stress. Stress is equal to force per unit length, let's say. So that is the stress we are applying. And what is the effect? Elongation, whatever. Strain is the effect. Change in length by original length. So this is cause and this is effect. So when you draw a graph, you have to take stress on x-axis and strain on y-axis. Right? The cause should be on x-axis and the effect should be on y-axis. So what happens? In the proportional region, in the Hooke's law applicable region, stress is directly proportional to strain. So as stress increases, strain also increases. But after certain time, what happens? The elastic limit breaks. So the spring will be permanently deformed, and there will be a more strain even without application of stress. So after a permanent deformation, what happens? Even for this less amount of stress, you get more stress. So that is what the graph says. But during our intermediate +1 +2 studies, the graph you might have studied is You might have taken strain on x-axis and stress on y-axis. So which is not acceptable to physics, right? Then why is this? So why people are studying that? What is the equation that we can write here? Strain is proportional to stress. What is the proportionality constant? 1 by modulus of velocity 1 by elastic modulus times stress. Let's say if it is Young's modulus, it is linear stress by linear strain. So how do you get that? Elastic modulus is given by stress by strain. So if you take the slope of this graph, what do you get? Slope is dy by dx, which is stress by strain. Which is directly equal to modulus of elastic modulus. So if you plot the graph by taking strain along x-axis and stress along y-axis, the slope of the curve directly gives you elastic modulus. I mean, that is actually a parameter required for engineers. So in engineering physics textbooks, you will see a graph like this, strain versus stress. Whereas in standard physics textbooks, the graph will be stress versus strain. Okay, so that is a parameter they require. So they are plotting like that, taking strain on x-axis and stress on y-axis. But standard physics won't allow that. And there are some cases where even in physics you may need to plot a graph between strain on x-axis and stress on y-axis. Okay. There are the cases where strain relaxation experiments are there, where when you apply some strain, when you apply some stress, the system will, let's say this is the stress and this is the strain. So when you apply some stress, some strain will be produced. I am studying it as a function of time. And as a function of time, what happens? You may not require the same amount of stress. The stress value may get reduced to keep the same amount of strain. So here stress is the cause and strain is the effect. So strain relaxation. So what happens? Once I start pulling a rubber band and if I wait for some time, what happens? Once this stretch becomes used to that rubber band, I mean once it may get permanently deformed, what happens? You don't need to apply the same amount of stress. You can reduce the stress by keeping the strain constant. So now what is the study here? How much amount of stress is required to keep the same amount of strain is the study here. So what is the dependent variable and what is the independent variable in this story? So the title of the experiment is strain relaxation. So in strain relaxation experiments, we are studying the amount of stress required to keep the amount of strain constant. So this is a dependent variable, this is independent variable. So in this study, strain will be along x-axis and stress will be along y-axis. So that is how, depending on the situation, you should be able to decide what to keep along x-axis and what to keep along y-axis. So it is always cause or independent variable should be along x-axis, and effect or dependent variable should be along y-axis. And these are some of the exceptions.